Welcome to the session about reactive Slick for database programming. My name is Stefan Zeiger. I'm the tech lead for Slick and the original developer since 2008. And I'd like to show you the cool new stuff we're doing in Slick 3.0, which is a big departure from what we've worked on so far. So the main thing we're doing here is to give you a completely new API for executing database actions. Previously, you had these invoker and executor classes, and they all used blocking I/O, so they blocked your caller thread, and you had a database session that you passed implicitly. This stuff is all gone now. It's actually deprecated now and will be removed in 3.1, which is also supposed to be out pretty soon. So execution in the new API is completely asynchronous, using Futures and Reactive Streams. This does not necessarily mean that it's non-blocking, because we're using JDBC under the covers, at the moment exclusively, but that's also something we want to change eventually. But still, from your point of view as an application developer, you don't have to deal with blocking anymore, so this will fit much better into your existing non-blocking Play and Slick applications. Play and Akka applications, of course. So why do we actually want to do this? Well, the reason is application performance. You want your applications to perform well. So how do you go about that? Well, you keep your CPU busy, right? That's easy. Utilize all your resources to the max. Except if you have blocking I/O, it's not actually that easy. Let's say you have 50% of your time doing computationally intensive stuff and 50% of your time doing I/O, then you're only using 50% of your CPU and just waiting for the rest of the time. Now, if you add a second thread, you're not using 100%, you're using 75%. So if you want to get incrementally closer to 100%, you have to add a lot of extra threads if you mix I/O and CPU stuff. And there's a problem with that, because threads are not free. They are reasonably priced, I would say, as far as old web stuff was concerned. Like when we started doing this with Java in the 1990s. But now that we have much larger scales to deal with, we get to see the problems with threads, because the more threads you have, the more context switching you get. When one CPU has to switch between different threads, and it has to evict the cache lines. And this is actually quite an expensive operation. So if you switch around a lot between many threads, it will really slow down your application. And there's also a memory overhead. It may be just a few megabytes, but still, if you want to serve like tens of thousands of connections, and you'd have tens of thousands of threads for that, it still adds up to a considerable amount. And of course, more thread memory also means more thrashing of your cache lines, which is really inefficient. And finally, if you want to communicate between threads, you usually do that with blocking. So you get lock contention, which is also expensive. So all in all, this does not scale very well. But it's probably not news to you, because you're already writing applications with Play and Akka. So you're used to doing non-blocking stuff. And you're used to avoiding threads and having more efficient means of scheduling. So just like this hamster, who's really busy there in his wheel, but doesn't actually go anywhere, you won't go anywhere if you only try to maximize the CPU. You also have to be efficient. You have to do the right stuff and not waste your resources. So, staying in the animal kingdom, there's of course a big elephant in the room, and that's blocking I/O. Because, as I said, we're still dealing with JDBC, and JDBC is blocking, and there's not much we can do about that, except for writing our own native drivers and avoiding JDBC entirely. But how much of a problem is that really? Because threads in small numbers are not that bad. So let's see how many threads we need by starting with the connection pools. Here's a simple web application architecture. You just have a simple one single server, and you're serving a number of clients which connect to the server, and you have a database and a connection pool in between. And here are the connections that pass through your pool. They're the same number on both sides, so your pool makes sure that you get connections from it instead of having to connect to the database again and again, but it's still a one-to-one mapping. You get one connection to the pool, which comes directly from the database. And of course, if you do blocking I/O, that means for each one of these connections, you have one blocked thread waiting for I/O on that connection. So how many of these connections do you need? Let's do a little quiz here. We assume we have a database server, latest i7 or whatever you want, 4 cores, 8 threads. You have 2 enterprise-grade 15K SAS drives in a RAID 1 configuration, so mirrored for data safety. And you have an app server which is strong enough not to be the limit here. And you want to serve 10,000 client connections concurrently. How big should your connection pool be? Should it be 10, 100, 1,000, or 10,000 connections? Let me see a show of hands. Who thinks 10? A few people. Okay, 100. A lot more. 1,000. Oh, a bit less. And 10,000? I see at least 2 guys there. Okay, so the answer may be a bit of a surprise to many. Frequently connection pools are oversized. So the rule of thumb that we take from like the Hikari CP and Postgres documentation as a starting point for sizing your connection pools is the number of CPU cores times 2 plus the effective spindle count of the disks that hold the working set. So in our case, we have 4 cores and we have 1 effective spindle because the 2 disks are just mirrored, which gives us 9 connections as a rule of thumb. So about 10. This would have been the correct answer. Okay, right. So we only need very few connections to the database. But why do we need many connections to our clients? Well, there's a big difference here. The clients will connect at their own pace. And all the clients are ready to connect to your application, and you need to be ready to accept them. And they're all ready to receive data whenever you can send it to them. So you don't really have a choice. You need to accept the connections, and then you can serve them one by one. Even though your application server has pretty much the same limits, because it also cannot do that many things in parallel. If you have 4 cores there, you won't be able to run more than 8 threads on them, right? But when it comes to the database, we have this under full control. We have a single application server connecting to a single database server. So we can control the scheduling. There's no need to send more requests to the database at any time than it can actually handle. Now this simple model, as I said, it's a rule of thumb. It works well for a typical scenario, but it can break down in some more extreme cases. And that's where actually really native asynchronous non-blocking database drivers could help us. And there are 2 scenarios in which this does not work well, and that's when you have lots of very small requests, because this blocking I/O and also the JDBC abstraction has a bit of overhead. And the other case is when you have a lot of contention in your database. You have transactions which lock rows, and these transactions run for a very long time, so you get lock contention. That means you'll be waiting for jobs running in the database, but they're not actually utilizing the database server. They're not doing any work, they're just waiting for something else. And we do not get a proper separation of I/O and CPU on the database. The database server will probably do that, it should do that, and it will know how to schedule stuff. But we never get that information, whether we're using a blocking or non-blocking driver. But what we could do with a native asynchronous driver is just throw more work at it at the same time and let it sort things out on its own. But still, for a typical scenario that you have in your web application, this rule of thumb actually works pretty well. And you don't need that many connections. So let's stick to this scenario and look at how we handle it in applications. In the traditional model, something like JEE, you're fully synchronous. So for each request that comes in from a web client, you create a new thread when you accept the socket connection. And then this thread will block on any kind of I/O, whether it's to the client or the database. So you get one thread per web request, and then when you want to hit the database, you have a contention for connections. Your get connection call to the connection pool blocks, because your pool size is only 10, and you want to serve 10,000 concurrent connections, so most of them will be blocked and just waiting for their slice of time on the database. This by itself is of course bad, and you all know that you shouldn't be using a blocking web server in the first place. But the worst part here is actually what happens when you put too much load on your database. What you really want is to be able to back off gracefully and like tell the client, hey, the database is too busy. We might wait 1 second and then we'll back off and give you an error page or let you do something else. But this is not possible in this scenario, because when you put more load on your database, what happens is that you have more blocked threads, and you're still creating more new threads when new requests come in. And creating new threads will make your application run even slower. So it just gets worse. So this clearly doesn't scale. So instead of using this one thread per request model, what you do is you use Play as an app server for your web application, and then you need to integrate this blocking database I/O into Play. And the naive approach is to just wrap your blocking calls into future of blocking, put your call inside. That's how you're taught to do it in a standard Play application. But there's still kind of the same problem. Because even though your web requests can be handled asynchronously on very few threads, as soon as you say blocking, this instructs the execution context, which is a thread pool running your code. It instructs this execution context to add extra threads, because the execution context is tuned for keeping your CPU busy. And blocking means this will block and not keep the CPU busy, so give me a new thread, because it shouldn't count against the total number. So you're adding more threads, which are blocked waiting for get connection. It's just as bad as before. One slight advantage is that you can configure this thread pool to have a limited size. As far as I know, it's not the default in Play 2.3, but you can configure it that way. And then you can at least fail more gracefully. But still, you have one thread pool for all of your I/O. So if you have multiple databases, you overload one database and your whole application again goes down, because all the other I/O cannot run either. So it's not ideal. So what you probably used instead with older Play versions is the Play Slick plugin, which integrates the old blocking Slick API into Play, and it's a bit more intelligent about this by using a separate execution context per database. That's already pretty good. There's a crucial difference to the previous model here, in that we now have contention for threads, because what we limit in size is mainly this thread pool. You have a thread pool of size 10 for your 10 connections, so you should ideally never be blocked on a get connection call. Instead, you don't even get a thread to run your call on. You just put your job into a queue from which the thread pool picks its work, and your get connection calls never block. There are still a few problems with this approach, though. First of all, we don't have a clean separation of I/O and CPU-intensive work in the old API. Take an innocuous-looking call like this table1.insert table2.something. So you insert data from one table or from a view into another table. What this call does is to compute a SQL query, a statement, and then perform the work. Send this to the database and do blocking I/O. It does both the CPU-intensive query compilation and the I/O in a single call. So you have no way to separate this the way you should. Also, we haven't really looked at streaming so far. What you get for streaming is an iterator in the old API. An iterator is for blocking reading. So you call next on the iterator and it might block. If you want to integrate that into a non-blocking application, you need something like a push-based stream or like Play's iteratees. And doing this conversion is either very complicated or very inefficient. At least if you know what you're doing. If you don't know what you're doing, it's probably both of those. But even if we leave performance issues aside, there's a more fundamental problem with the old API. And that's what you see in this DB with session call here. This can already be a problem in a synchronous application where you have a single thread. But as soon as you use futures, it's very easy to make mistakes here, because the with session call uses a loan pattern. You create a session for your database, which is a JDBC connection. When you enter this block of code here, and when you leave the block of code, you return the session to the pool. And you can only use it in between. But if you create a future, any database code in there will not have the session available anymore, and it will just blow up because the session has already been closed. Now the problem for this, of course, is that we have mutable state here. It's maybe not that obvious as having a var, because you don't really see the mutable state, but it's there. At this point here, the session is valid, and at this point, the session is not valid anymore. There's state in the session that has changed in between. So to solve this and make it more robust, we looked at how other programming languages with pure functional I/O do the same thing. And there are a few different approaches. One of them is particularly useful if we also want to do asynchronous I/O, because we could use effect types which are not there yet in Scala. We could use linear types which are not there. We could use an effect system which might eventually be there, but they still wouldn't help with the asynchronous part. So instead we reached for, let's say, computer science for 200. Anyone familiar with Jeopardy who'd like to solve this? Nobody? Yes, almost. When's the last time you watched Jeopardy? You need to ask a question. What is a monad? So, since I'm not doing a monad tutorial here, I don't want you to blame me for giving you a wrong definition. So we're just looking at Wikipedia. So Wikipedia says, in functional programming, a monad is a structure that represents computations defined as sequences of steps. And later it talks about programmable semicolons. That's good. I've been writing Java since 95 or 96, so I know what semicolons do. So let's look at semicolons. Well, not yet, but we'll get to the semicolons in a moment. If I did a monad tutorial, I might tell you something about collections as monads and about options and stuff like that, but it would just lead you down the wrong path, because you may think monads are actually collections or containers, but they're really just a special case. So we're going to look at a totally different monad, the state monad. So what we have here is imperative code. There's a reason the Haskell people like to call Haskell the finest imperative programming language, because with pure functional I/O and monads, you can really write imperative code. So what do we do here? Well, we have a state with an initial value. We get that value out, assign it to I. Then we set the state to I plus 3, get it out again, assign it to j, set it to j minus 2, get it out, assign it to k, and return it. A simple step of commands that we run one after the other. And we run this with the initial value of 41. And there's our state we put in, and we get 42. So that's a state monad. And it looks almost the same as this imperative code here, especially in Scala. You know, you see the get and you set. That's it. There's really not much more to it. So now we have a shiny new toy, the state monad. I needed to put ponies into my talk at some point. So let's look how you build it. So what you need for a monad is three things. First of all, a type constructor. So we have a state of something, in this case state of R. That's the monad part. There's also this S type, which represents the actual state. In our case, it's an int that we store in there. And if you look at how it's defined, extends function from S to S, R. you may already be able to guess how it's implemented and what it really does, because state is just a stateful function. You pass in the existing state into this function, and you get out a new state and whatever value you want to compute or return from it. So you just chain your state through a series of functions. So the next part we need for the monad is a way to lift a value into the monad. That's the apply method. We have that here. So apply is a state of S and R, and we take the existing state, we just pass it through, we don't change anything, and the value we return is this V that we pass in. Okay, so those are the two first parts we need for a monad. The rest here is not needed for a monad, but it's needed for the actual state because we want a monad to do something. So we need to be able to get the value of the state out, and we need to be able to set a new value. So to get the current value, well, we just return the state unmodified, and we also return the state as the value. And for setting the value, we do the opposite. We discard the original state. This is ignored. We return the new value as the new state, and unit as the value to be computed, because setting a variable returns unit, and as a side effect, it changes the state. And then we also have a run method that we saw, which is used for running the state, and this just is a function application. Our state is a function, so we apply that function, and in the end, we only return the second part. That's the return value. We discard the state that we get out at the end. There's one more bit we need to make this a monad, though, and that's the flat map call. That's what actually implements the semicolon. So how does flat map work? Well, we have our left side of the state flat map here. We call it self, and we flat map with a function that takes the return value of the left-hand side and computes a new state. So the way this works is that we start with the original state value. We apply this to the left-hand side, which gives us a modified state and a return value. Then we evaluate the function with the return value to compute the new state object that we want to apply to. And then we use this S2, the modified state, put that into the second part, into the right-hand side. And in the end, we get out another modified state and the final return value. So it's just threading the state through two functions. We also have a map method. We don't really have to look at it because the monads do not just need to have these three pieces. They also have to obey certain monad laws. And if they do, then you can always write map using flat map and apply if you have defined them. This is always the correct definition without even checking anything else. But how does the state monad help us with functional I/O? Because as we've seen, it is really purely functional code. There's no I/O in there. We're not really modifying any state behind the scenes. It's just function passing. Well, there's a quite similar monad, and that's the I/O monad. That's what you use in Haskell for actual I/O. So the code here looks almost the same as for the state monad. That's because it's supposed to do the same thing, just in a slightly different way. So again, we get our I value out and we set it to I plus 3 and so on. It's the same steps we did for the state monad. But when we run it, you see we run it on this new DB with a starting value of 41, and that's a var in this case. So that represents our database. This is actual mutable state. We want to mutate this while running the I/O monad. So let's look at the implementation here. The function that it extends is a bit different. This is just db to r. It's not db to db, r. That's because db contains mutable state, so we can just mutate it as a side effect. We don't have to pass this through. You just pass it in and mutate it as a side effect. So you can see this in the set method here. We have our db object and we want to set this value v, so we just set it. We don't have to return the new value. We're really mutating here. But the important thing is we're only mutating anything when we run this I/O. If you go back to this part here, this is still totally purely functional. There's no mutation happening here. We're only describing what mutation to eventually run down here when you say run. This is the part where the mutation happens. Let's take a look at flat map. This is also pretty much the same as for state, except that we don't need to thread the state value through anymore. So first we apply db to self, which does not return a modified db, but instead actually modifies this one. We pass this to the function f to construct the new state, or new IO in this case, and we apply it again, and this might also mutate the db. But still we first do the left-hand side, and then we do the right-hand side. And again, the map definition is totally standard. There's one part here that I don't really like yet, and that's the fact that we expose this function. We really want to hide this mutable state because we don't want you to just call this function yourself or implement it yourself. At least not that easily, that it's obvious in the API. What we can do there is to use a free monad pattern. So we reify the computations instead of just chaining functions together. There's an actual implementation class for each of the operations like flatmap, or also for the primitives like get and set. They all have separate classes that we can then match on a run-through in an interpreter. So here in this flatmap, we just create a flatmap object that captures this information. And then when you run it, you have an interpreter and you match on flatmap IO, and then you do whatever you have to do. But it's not in the signature anymore. This is just an abstract trait, and then we use the interpreter. There's another advantage apart from hiding this mutation and hiding the function, and that's the fact that we can have different interpreters, which is really useful in our case because we want one interpreter for computing a value directly as a future, and we want another interpreter for streaming. And these need to work in slightly different ways. So you can construct your stateful computation, your IO computation, in exactly the same way, and then decide if you want to compute the whole thing or if you want a streaming result. There's another monad that you're already familiar with, and you use that for asynchronous programming, and that's the future monad. You have the same combinators for that. And it's used in a different way, though. We cannot directly use it. We need a special I/O monad because future is used for concurrency, not for strict sequencing. There is a sequencing part that's inherent in any monad. You can see this here. There's a flatmap call. That's what makes a monad. And in order to compute something here, you first need to get the result of the left-hand side. Even if you discard it, it doesn't know that you discard it here. So there's always a sequential part in every monad. But whether this F2 actually starts a new computation in a future, or maybe it already has a value, or it's a computation that's already running on another core and may eventually produce a value, you don't know that here. Only the composition of the results is sequential, but not the actual computation. So futures are used for a different purpose. You use them for concurrency, whereas I/O is used for sequencing, when you want to guarantee that things run in a sequence, which you need like for transactions. So in order to work with both of these, you can first compose your code in DBIO, and then you can compose further in future, depending on what your needs on this composition are. Here we have the actual types that are really used in Slick. So there's a DBIO action. You can actually also call this DBIO of R. We can just ignore the rest here. And there's a run method, just like we had in our simple demo for state and I/O. And this run is defined on a database. So you run your I/O code, your DBIO, on a database, and the DBIO of R gives you a future of R. So you run it through an interpreter, which actually starts the computation, and then you get a future, and eventually this will complete and give you a value. So, of course, all your basic database operations already give you a DBIO, but you can also take an arbitrary asynchronous computation and lift that into DBIO. So you have something that gives you a future, and you want to use that as part of a transaction. So you log some rows in the database, read them in a transaction, then you run some asynchronous computation somewhere, which gives you a result, which you need to pipe back into the database to update that data. You can do this by lifting your future into DBIO, composing it sequentially, and eventually running the whole thing and getting a future out that you can then further compose concurrently. So let's look at some actual combinators, how to compose these DBIO operations, and look at some actual operations. If you used Slick before, the right-hand side here should look pretty familiar, because the API there is almost the same as in the old versions. You have tables, X's and Y's, and you have a .schema, which was actually called .ddl before, which gives you the DDL for the tables, and you can concatenate them and then create the DDL in the database, and you use the ++ equals operator to insert data into these tables. Previously, those were methods that actually ran this DBIO action directly and gave you the result. Now these methods just give you a DBIO action, and then you can use the for comprehension to compose them. That's the most general way of composing DBIO actions. In this case, though, we don't really need it. You can see here that we discard all the return values. We don't care what they return. So we don't really need the for comprehension. So there's a simpler way. We can use the and then operator, also available as this double right arrow. And this is actually another operator from Haskell. It's used in the same way for monads there, for any kind of monad. Here it's specific to DBIO. It first runs the left-hand side and then runs the right-hand side. It's slightly different than the first action because it actually returns the value of the right-hand side. So ++ equals by default returns the number of rows inserted. This should be 3. So this will be a DBIO action of int that returns 3. But we don't care in this case, so it doesn't matter what it returns. If you don't care about the return value, you can go even further and use dbio.seek, which just takes a var args list of any kind of DBIO action and in the end returns unit. That's very convenient for composing large numbers of operations. So why would you choose one or the other? Well, in general, what you want to do is pick the most specific one. In particular, use and then or dbio.seek instead of flatmap, because there's a performance difference here. You can see that in the signature of and then, we have a left-hand side, of course, which you call this on, your DBIO of R, which already exists. You have an object that you call the method on, and the right-hand side is a DBIO of R2. That's another object that exists. So if you go back to these insert operations, these operations actually have to compile the SQL code to do the insert. So in this first expression here, because it's a monad, you first need to run this operation before you can even compute the second one. And then you can compute the third one. You cannot compute them up front. But if you use and then, it computes everything up front. It's not lazily evaluated. These values are all strict, so it's the most efficient way to do this. Sometimes, though, you really need the result of the left-hand side, and then you need to use flatmap. There's nothing wrong with doing that. It's just that it's more efficient if you use the other methods. And you can see in flatmap, we also take an execution context here for asynchronous execution. So this is what we use to run the function on. You give it a function. You write arbitrary code here. And because we run the DBIO actions on a separate database execution pool, on an execution context, a separate thread pool that's only supposed to be used for database I/O, we do not want to run your user code on this thread pool because it would disturb things and mess up the computations of how many threads we really need in this pool. So instead you give it this execution context, and then it will run your computation on your implicit execution context and then pass the result back to the database pool. And in the and-then case, we don't need this. So we can go even further. If you have two database I/O operations and you run them next to each other, and you use and-then instead of flat map, they can even be fused. So that's almost like writing imperative blocking code, because you don't have to use any futures in between to pass the values behind the scenes. You don't have to move a state from one thread to the other. It just runs them on the same thread, on the same session directly in the most efficient possible way. Okay, that's what we can do for immediate evaluation. Let's look at streaming results. So we're now doing a real query, not just creating and inserting. We have a table of orders. We filter for the ones that have been shipped, and we project to the order ID. So we get a number of int values for the order IDs in this case. This is a query, and we can now convert it to an action. That's different from the old API. You had a run method that just ran the query. Now you get a result method which converts it to a DBIO action. And you can use the db.run method that we've already seen to evaluate this and compute the result, which will be a seek of int in this case. But if you have a large number of results, you may want to get them in a streaming way. So instead of db.run, you can use db.stream, which is a slightly different interpreter for this monad. And it gives you a publisher for a reactive stream. So we're using the new Reactive Streams API that you may have seen in Matthias' talk just before lunch in this room. And we implement a publisher for the database results. Actually, we have a special database publisher that adds some convenience methods like this for each here. But for anything serious that you want to do with this, you will use something like Akka streams for actual stream processing. We're only concerned with getting the data in a streaming way out of the database, and then you use Akka streams for everything else. And of course, Play 2.4 also supports reactive streams in addition to iteratees. And in a future Play version, this is supposed to become the default. So you can directly interoperate between Slick, Play, and Akka streams. So the main feature that reactive streams give you is asynchronous streaming with back pressure handling. So let's look at what this means in the context of database calls. Here's the synchronous case. Everything is blocking. And you never even think about back pressure handling because it's built into this model. It's absolutely not a concern. So we have our database thread here, and we do a blocking call to the database, and when that returns, we do a blocking call to the client, like writing to an output stream that goes over the network. And then we do another blocking call to the database, and so on. There's no problem with back pressure. Everything happens sequentially. Now, if we do a naive approach for asynchronous streaming, we get something like this. We have a blocking call to the database, it returns, we send it to the client. That's a fire and forget call. It's asynchronous. Then we immediately do the next blocking call, and so on. But we do not know if the client can actually accept data at that rate. Can the client send it fast enough over the network, for example? We have no idea. And there's not much the client can do if it cannot keep up with the data. Either it has to drop data or try to buffer everything. There's no back channel to make us go slower. And that's why we need reactive streams to add this back channel. So now we do something like this. This is the simplest case where the client always requests a single element from the stream. So at this point, he requests the first element when we start the stream, and immediately we go to the database. These are actually independent actions. They just happen to be at the same time when we start the stream, but they run on different threads. So we go to the database, we fetch the data, and we send it to the client. And then we immediately go back to the database again. Even though the client has not indicated that it wants more data, we always fetch the next element ahead. And then at this point, we have the next element, but the client is not ready yet to receive it. So there's nothing more for us to do, and we don't want to block a thread. What we want to do is keep the database pool blocked only on actual database I/O. So we just store a continuation of the stream to be used again when the client is ready, and we return the pool into we return the thread into the pool so that another database job can run in this thread. So here the client is ready again. It requests one more element. We immediately send that element to the client and request the next one. And then all over again. Now this time, the client already signals that it's ready to receive another element before we get it from the database. So in this case, we can just continue sending. And this is a very efficient loop that we run here. It's basically synchronous like an iterator with very little overhead on top of it. So as long as the client can keep up and always requests more, we can very efficiently stream this data to the client. And as soon as the client is not ready to receive it, we store a continuation and free up the thread for other database work. Now this is still the most inefficient way of using this, almost running in lockstep. We can go further. The client can request 2 elements at a time. It's a trade-off you have to make. You need to buffer some more data, but you don't need to store so many continuations and do so much context switching. But of course, if you use something like Akka streams, that's already built in, so you don't really have to care about this buffering. It's all handled automatically for you. So how does this look in the code? Well, we've seen the run method before. It takes a DBIO action where we use this first parameter, r, to return a future of r. Now for stream, that's where we care about the second parameter. This is a streaming of t, and it gives us a publisher of t. So it's set up in a way that every streaming action can also be used as a no-stream action. That's what we take up here. So every streaming action can also be fully materialized. And all the collection-valued queries that you run that return a result set where you actually have individual rows to read, they're all marked as streaming. And there's one important difference between stream and run, and that's the fact that stream does not actually start the database operation yet. That's due to the way reactive streams work. This publisher is just a placeholder for the operation, and once you attach a client, a subscriber to this publisher, that's when your action really runs. So if you want to try this stuff yourself, we have a nice activator tutorial called Hello Slick, Slick 3.0. There are different versions for the different releases of Slick. You want the one for 3.0, and you can go to typesafe.com/getstarted to get Activator, and then just download this from the template catalog and run it immediately. So that's all I have for reactive Slick. I'd quickly like to highlight some other new features we added in this 3.0 release. Maybe you've used outer joins before, and they've been a huge pain in the ass so far in Slick because it gets the types wrong. Now you don't have to understand all the details here. We have a class row which extends a table of data, so we're mapping this to a data case class. And we have 2 instances of this type, X's and Y's. Now we do a left join on it. So X's, left join Y's on whatever criteria. And with the old left join operator, what we get is a seek of tuple of data and data. But that's wrong, because on the right-hand side, it's not really a data, because a left join can produce a null row on the right-hand side, so we don't get anything. What we really want is a tuple of data and option of data. But we didn't have the right encoding for this so far in our API. Now we have it. There's a new Now, this is what you previously would have to write. It took me about half an hour and 10 tries to compile this to actually get it right. So that's not something you want to do. So with the new API, there's a join left operator, and the old left join is deprecated. And this actually gives you a seek of data and option of data. So you can construct outer joins over multiple tables very easily, even in the presence of mapped data. Another cool feature that was developed as part of a Google Summer of Code project last year is statically checked plain SQL. So you've probably seen something like this before. We have a plain SQL string interpolator called SQL, where you can just put your SQL string in and then say as tuple of int and string in this example. And this gives you a DBIO action that you can run to directly run the SQL code. But of course, there's no static checking. Now we have a new T-SQL operator. You can see there's no ask call anymore. What this actually does is it uses an annotation in your code to find out how to connect to a test database at compile time in the Scala compiler via a macro, and then asks the database to check that code, and you get a proper error message from the Scala compiler if it doesn't check. The database will infer the type, and then we translate that back into a Scala type, and it knows that this returns a tuple of int and string because that's what select ID, name actually returns. So that's a pretty cool feature. We also use Typesafe config now to read our configuration, and you can configure connection pools directly in Slick. And this is important because tuning connection pools works differently than what you read in all the connection pool tuning tutorials. They're all targeted at the blocking method, like JEE, where you have contention over connections. So you limit the number of connections in the pool. That's not something we do. We limit the thread pool size and then give you more connections in the pool. So we have our own way of tuning this, and the most important parameter that you can set there is the thread pool size, and everything else is derived from it. And that's also what you'll use when you work with Slick 3.0 and Play 2.4 and the new Play Slick plugin. I think that's version 1.0 now. It also uses Slick's own way of creating a connection pool. But you can still use Play's evolution feature because it will now tie into Slick's pool. So that's what I have for Slick 3.0. The major feature coming up in Slick 3.1 is a new query compiler backend that I'm working on at the moment to create better SQL code. This is a real output from Slick 3.0. That's a join over 3 tables. It looks rather horrible. You can't see what's going on there. And this is what it looks in my working branch. So that's the Slick 3.1 version. Now you can actually see what it's doing. In most cases, it's just to make it more beautiful. But if you're using MySQL, this actually matters because the performance is really horrible with this version because MySQL doesn't have an optimizer worth mentioning. And this version should be pretty much ideal. So we're getting rid of all these unnecessary subselects. So that's all I have so far for you. Thank you for your attention. If you have any questions, I think we have some time left. I'm not sure. Do we?
So if I understand correctly, you have a separate thread pool for the database communications, and then you have a thread pool, connection pool sort of behind it.
Yes, that's right.
Have you considered options to sort of collapse the two, so do you just have one connection per thread in that database thread pool?
Yes, so that's a question that comes up frequently. We do not have a one-to-one relationship between the threads and connections because you have situations where you want more connections and threads. For example, in the reactive stream that you've seen, if you run this in a transaction or even just a regular stream, you suspend the stream at some point, but you're still connected to the database there. But the thread pool is free to run something else, so you need more connections in your pool than streams. The number of threads limits how much you can run in parallel. The number of connections limits how much state you can keep in your database and on top of what you can run in parallel.
How is it working with transactions? If you have this asynchronous approach, then you always have this problem that you keep the transactions clean.
It's actually much nicer now in the new API to compose this. You just say .transactionally on a DBIO action, and it runs a thing in a transaction. So you can easily compose these, and it's still just a DBIO action that you can compose further.
Just want to expand on the question that was asked. Normally, if you run Slick within a J2E server, and JTA normally would tie your connection to the thread local for transaction demarcation. And if you're using Futures to compose access to the database, how do you demarcate multiple access across one transaction?
So we're not really focusing on like a JEE or JTA use case. We really want to make it as good as possible a fit for asynchronous applications. What you could do, of course, if you want to hack something like that yourself, is to just put your own executor in. So you could replace the standard executor that we use with one that does everything on the same thread, and then you can put this into a blocking application. But it's not something we support out of the box.
Thank you. Is there any work done to use something like Akka IO and have a really low-level implementation of asynchronous database driver?
We're going to look at a really native asynchronous database access really soon, like over the next half year. I'm not sure if it will be Akka IO or some other way, but we want to do non-blocking IO. Okay, thank you everyone.